Hi class, let's quickly revisit the definition of differentiability of a function at a point and then continue with our session from where we left in the last lecture. I say a function fx is differentiable at a point x equals a of its domain when limit x tends to a fx minus f of a upon x minus a exists finitely, right? And then we said this limit existing means this limit existing from the left of a and this limit existing from the right of a, and both of them are equal to the same number, which is this, right? And therefore, alternatively we define left hand derivative of f at a. What was that? Limit x tends to a from the negative f of a minus h minus f of a whole upon a minus h minus a, and then we replace x tends to a from the negative from h by h tends to 0. Eventually getting limit h tends to 0 f of a minus h minus f of a whole upon a minus h minus a gives you minus h. And similarly we defined right hand derivative of f at the domain point x equals a as what? Limit h tends to 0 f of a plus h minus f of a whole upon a plus h minus a, which is just h. Fine. So having defined the left hand derivative of a, left hand derivative of f at a and right hand derivative of f at a, we said LHD of f at a should be equal to RHD of f at a is what is the meaning of this limit existing finitely. Fine. Now what we discussed in the last lecture was that whenever a function will be differentiable at a point, it will necessarily, compulsorily be continuous at that point. I also explained you a geometric, natural, intuitive way to understand this particular concept. Moreover, we formalized it by proving it in complete manner. So what did we learn? We learned that differentiability at a point implies continuity at that point. Fine. Once we had understood this by formalizing a proof of this, in fact understanding it in geometric sense, because when you say differentiability at a point, you need chords to be existing on the left hand side of that point or on the right hand side of that point on the curve. For chords to exist on the left hand side and right hand side of the point at which tangent you wish to show is existing, curve should exist on both sides of that point, which implies continuity at that point. That means there is no break. The curve is not broken at the point at which you are testing your differentiability, or at which the function is already differentiable, which therefore implies that the function is continuous at that point. Okay. And I told you, if differentiability implies continuity, is it true that continuity implies differentiability? Answer was a big no. Continuity does not imply differentiability. A function may be continuous at a point but may fail to be differentiable at the same point. Well, you might ask me, what is that function, where is that function which possesses the feature of continuity at a certain point of its domain, but when I check the differentiability of the same function at the same point at which it is continuous, it's not differentiable. That means corresponding to that point, the curve is unbroken, there is no break, there is no hole, there is no gap. A continuous form is there in the curve corresponding to the point, suppose A, of the domain. But when I go and see corresponding to the point A at the point A comma f of A in the graph of the function f, I cannot draw a unique tangent. Yes, either there are infinitely many tangents to be drawn, right? That means somehow there is a corner point in the graph corresponding to the point A. Okay, that is why the function is continuous at that point but not differentiable. Well, the example of such a function is fx equals mod x for all x belonging to R. This function is continuous. This function is continuous at x equals 0 point of its domain, but not differentiable at the same point. Fine. If I make you recall about the graph of the modulus function, the graph of the modulus function was like this. This is the graph of fx equals mod x, where this is your x-axis and this is your y-axis. Fine. And this is your 0, 0. Okay? If this is fx equals mod x graph, you can see there is one corner point in the graph. The corner point is this. Corresponding to the point 0 in the domain, 0 comma f of 0, which is 0 comma 0 is a corner point in the graph of, in the curve of y equals mod x. Definitely at this point infinitely many tangents can be drawn to the curve y equals mod x. That means function is not differentiable at 0. But if I talk about the hole or a gap or a break in the graph of the function, there is no break. I can take my pencil, in one go I can complete the drawing of this graph. I will not have to pick up my pencil in way between in order to complete the drawing of the graph. Because there is no hole, no gap, no break, it's an undisturbed graph, completely continuously drawn. That means it is continuous, but because there is a corner point, that's why it's not differentiable at the point 0. So that's why it's written the function is continuous at 0 but not differentiable at 0, because corresponding to 0, 0 comma 0 point in the curve, over there the function is continuous. There is no break, no hole, no gap. But if I talk about 0 comma 0 point on the curve, it is a corner point and therefore there can be infinitely many tangents which can be drawn, because of which it's not differentiable at 0. Fine. Already while studying continuity, we have proven that modulus function is always continuous. So, we know modulus function is an everywhere continuous function. Okay, modulus function is an everywhere continuous function. That means it is continuous on the entire real line, which implies fx equals mod x is continuous on the entire real line, which implies fx equals mod x is continuous at x equals 0. If it is continuous for all real numbers, it is definitely continuous for 0. Fine. I have to show this function was continuous at 0 but it is not differentiable at 0. So intuitively again by just the graphical approach we have understood that because 0 comma 0 is a corner point, function is not differentiable at the domain point 0. But formalized approach will be what? Any function is differentiable at a point provided left hand derivative of f at that point is equal to the right hand derivative of f at that point is equal to a finite value, right? That is what is the condition. We learned it in the definition of derivative. And therefore, over here, I will be now calculating the left hand derivative of mod x at 0, then right hand derivative of mod x at 0, and we will see that they both do not come out to be equal, and then I will tell you the reason also. So let's begin with left hand derivative. Left hand derivative of fx at x equals 0 will be what? Limit h tends to 0 f of 0 minus h minus f of 0 whole upon minus h. Right? Just see. H tends to 0, f of a minus h minus f of a whole upon minus h. Here my a is 0, so limit h tends to 0, f of 0 minus h minus f of 0 whole upon minus h. Right? If fx is equals to mod x, f of minus h, this is minus h only. I can write it as limit h tends to 0, f of minus h minus f of 0 upon minus h. F of x is mod x, so f of minus h is what? Limit h tends to 0, f of minus h is mod of minus h minus f of 0 is mod of 0 upon minus h. How does mod x function behave? Whenever you are in the negative side of the real line, f of x is minus x, right? So over here, f of or mod of minus h is minus of minus h. Why? Because h is positive. H is positive, minus h is negative. So mod of a negative number is minus of that number. So minus h is negative. So mod of minus h is minus of minus h, which is h. H minus mod 0 is 0. You know f of 0 is 0, mod 0 is 0, whole upon minus h. This is what? What will this become? This is limit h tends to 0, h upon minus h. Because h is positive, I can cancel these h and I am going to be left with limit h tends to 0 minus 1, which is minus 1, because constant function is continuous. Limit of a constant function at any point is the same function, which is minus 1, the same constant. Okay, so left hand derivative of f at 0 is coming out to be minus 1. Let's focus on the right hand derivative of f at 0. Fine, right hand derivative. What will this be? Limit h tends to 0, f of 0 plus h minus f of 0 whole upon h. Okay, what will this be? Limit h tends to 0, f of 0 plus h gives you f of h minus f of 0 whole upon h. Now if f of x is mod x, f of h is mod h. So this will be limit h tends to 0, mod h minus mod 0 upon h. H is positive, so mod h is same as h. This will be limit h tends to 0, mod h is same as h, mod 0 is 0, whole upon h, which gives you limit h tends to 0, h upon h, which is limit h tends to 0, 1, because I can cancel them because they are non-zero, which is just 1 because it's a constant function. That means right hand derivative of f at 0 is coming out to be 1, left hand derivative of f at 0 is coming out to be minus 1. So what I have got is left hand derivative of f at 0 is not equal to right hand derivative of f at 0. And because this is what is holding, that is why, what is it that I have? My function fx equals mod x is not differentiable at x equals 0. Fx equals mod x for all x in the collection of all reals is not differentiable at x equals 0. Fine. Now over here we had proved that my function fx equals mod x was continuous at x equals 0. But we have landed in the proof and the conclusion that fx equals mod x is not differentiable at x equals 0. By 1 and 2, the result is proved that continuity need not imply differentiability. Understood? Why did this happen? See, what is tangent, or what is, I should say, differentiability meaning? This is my y equals mod x graph. Fine. What is this line? If I try to focus on just this line, what is this line? This is y equals x and this is y equals minus x. Right? This is y equals x, y equals minus x for all non-negative reals here and for all negative reals here. Okay. What is the meaning of differentiable? Function is differentiable at the point 0. That means the derivative of f at 0 will be equal to the slope of the unique tangent at 0. Right? This is one tangent which can be drawn at 0. Right? Isn't it? This is one tangent to the curve which can be drawn at 0. What is the slope of this tangent? Well, slope is 1. If you remember, y equals mx plus c is the equation of the straight line with slope m. So here it is y equals to 1 into x plus 0, slope is 1. Similarly over here, y equals mx plus 0, m is minus 1. This is another tangent which can be drawn. Its slope is what? The equation of the line is y equals minus x. Slope is minus 1. That means the chord that you have drawn on the right hand side of the point to the curve, it's limiting. It's the slope of the chord, its limiting position is basically giving you the slope of the tangent at the point 0 to the curve from the right hand side, which is 1. Similarly, this is one chord I can consider which is drawn to the curve on the left hand side of the point. Fine. Limiting position of this chord is actually giving me the slope of the tangent to the curve at the point 0, which is coming out to be minus 1. That means from the right hand side slope is different, from the left hand side slope is different. That means there is no unique tangent. I told you if there is a unique tangent, the slope from the left and the slope from the right are exactly the same. That means here there is no unique tangent. If there is no unique tangent, function is not differentiable. Fine. There are infinitely many tangents which can be drawn over here. Right now just 2 of them giving 2 different slopes suffice to conclude that the function is not differentiable at this point. Fine. Let's proceed further with some more results. Till now we have done differentiability at a point. Well, we have also discussed about differentiability of a function on a set. Right? When I am saying function is differentiable on a set, what I am trying to say is the function is differentiable at each and every point on the set. Fine. So, alternatively, basically there is one set which specifically I would like to discuss. A function fx is differentiable on closed interval a comma b. A function is differentiable on closed interval a comma b. Now see, why is there a problem over here? Or basically let me write the statement, then I'll explain you the meaning of the statement. A function fx is differentiable on ab when fx is differentiable on a comma b and right hand derivative of f at a exists finitely. And left hand derivative of f at b exists finitely. Fine. Now, one thing which you have to recall about differentiability is when a function is differentiable at a point, curve should exist on both sides of the point, right? One thing. Secondly, the point, suppose at A you want to check the differentiability, then at A comma f of A, this point A comma f of A should not be a corner point. These two things. That means if I am talking about closed interval A comma B, suppose this is A, suppose this is B. Corresponding to this point is, suppose this is some function's position, and here you have this as f of B. So this is f of A, or I should say A comma f of A, and this is B comma f of B. Correct? This is how the graph will look. Now see, at all the points, now see, just ignore for a second, ignore the endpoints. Ignore the endpoints, that means ignore this and ignore this. For all the points which are in between A and B, I can talk about differentiability of the function at all these points. But when I talk about the function's differentiability at these points corresponding to A comma f of A is a corner point of a graph. Is there portion of the curve here? No, there is no portion of the curve here. There is portion of the curve only on one side. If I talk about B comma f of B, there is no portion of the curve here, only the curve is here to the left of this point, right? Therefore, we cannot talk about function being derivable at A and at B. We can only talk about function being derivable at open AB. But at A, we can talk about the right hand side differentiability. At B, we can talk about the left hand side differentiability. Because there is some portion of the curve on the right of A comma f of A, and there is some portion of the curve on the left of B comma f of B. So that is what happens to be the meaning of this statement, because it is not possible to talk about function being differentiable at A and at B, which are endpoints of this domain, because these endpoints are going to correspond to give you two corner points in the curve of y equals fx. And the moment you have corner points, you directly say the function is not differentiable, right? But if right hand derivative of f at A is existing, left hand derivative of f at B is existing, I am not concerned with right hand derivative of f at B, I am not concerned with left hand derivative of f at A. Just right hand derivative of f at A should exist, left hand derivative of f at B should exist, and the function should be differentiable at open AB. Because at open AB I have no problem, right? At open AB no points are corner points. That's why no problem to check differentiability. These are the three conditions which are going to prove that the function is differentiable on closed AB. Understood? Apart from this, a function is differentiable on a set if it is differentiable at each and every point of that set. Fine. Therefore, I can say over here what we did was differentiability at a point implies continuity at a point, at the same point, but continuity at a point need not imply differentiability at the same point. Similarly, I can extend it to if a function is differentiable on a complete set of domain, this implies that the function is continuous on the same set of domain. But if a function is continuous on a certain set of domain, this need not imply that the function will be differentiable also over the same set of domain at all the points of that domain. Fine, so this is how we can generalize. Apart from this, all of us know about some common differentiable functions. What do we know? We know that a polynomial function then a constant function fine, then a logarithmic function then exponential function then trigonometric function all of these we know are standard differentiable functions. They are differentiable functions over their respective domain. Right? Moreover, we also know that sum, difference, product, quotient, composition of differentiable functions is differentiable. Fine. We have done all this in 11th standard, no doubt about this. Let's proceed further and touch the composition portion of this algebra. Here we will be basically learning about a certain rule which is very, very famous in differentiation, which you should be very nicely aware about, and that is called the chain rule. Let's focus on this now. What does the chain rule say? It says, let f and g be two differentiable functions. These are two differentiable functions already given to you. Let these be two differentiable functions. Then FOG of x, the composition, is also a differentiable function. Now you would say, well, we know this. We know that composition of two differentiable functions is differentiable. What is so special about it coming under the chain rule? Well, you know that if f and g are differentiable functions, they give rise to newly created functions known as f dash x and g dash x. Right? F and g are differentiable functions. When I am saying, that means they are differentiable over their respective domain. Fine? If f and g are differentiable, that means they are giving rise to newly created functions f dash x and g dash x. If I am saying FOG is also a differentiable function, what I am trying to basically make you stress on and focus on is that even FOG is going to give rise to a newly created function known as FOG dash of x. What will that be is what gives the chain rule. So it says FOG dash x is equals to f dash gx into g dash x. Yes. This is what is the formula to compute FOG dash of x for every x in the domain of FOG. Fine. Now what is this trying to say? This is saying d by dx of FOG of x is d by dx of f of g of x. This is what is the definition of FOG of x. What you do is, differentiation of f of g of x with respect to x is equal to differentiation of f of g of x with respect to g of x into differentiation of g of x with respect to x. Understanding? Differentiation of f of g of x with respect to g of x. Right now this is sitting as the variable portion. So with respect to that variable you differentiate. Then the thing which you have considered as the variable, differentiate that with respect to its variable, which is x. Understood? That is what is the meaning of chain rule. So in the form of chain, this differentiation is carried forward. Let's proceed with the proof, and then I am going to generalize it for you, and then we will be dealing with an illustration over this. Let f and g be differentiable functions. Now when I'm just saying differentiable functions means they are differentiable over their respective domains. This implies f dash x or d by dx of fx. At every point x, for every point x, f dash x is existing, which is given by which formula? Limit h tends to 0, f of x plus h minus f of x whole upon h. Why? Because if this limit is existing, it is equal to the left hand derivative equal to the right hand derivative. So the limit can be equal to either LHD or RHD. So in particular, I can say f dash x is given by this formula, right? Because they are equal, LHD or RHD. And g dash x, which is d by dx of gx, is what? Limit h tends to 0, g of x plus h minus g of x whole upon h. This is existing for every x in the domain of f. This is existing for every x in the domain of g. Fine. I have to show FOG. FOG we know is differentiable. Don't we know? FOG we know is differentiable. I have to basically talk about FOG dash of x. Right? When will this function exist? If at every x FOG is differentiable. Right? If at every x FOG is differentiable means left hand derivative of FOG at x is equal to right hand derivative of FOG at x. Let's talk about in particular the right hand derivative of FOG at x. Fine. Let's talk about this. This will be what? Limit h tends to 0, FOG of x plus h minus FOG of x whole upon h. For a certain specific number in the domain of FOG, that is x, this is the right hand derivative of FOG of x at that specific x, which is FOG of x plus h minus FOG of x whole upon h, right hand derivative. This is what? Limit h tends to 0, f of g of x plus h minus f of g of x whole upon h. Fine. What is it that I am going to do now in order to manipulate this expression? This is what I have with me. Why don't I do this? What is it? Limit h tends to 0, f of g of x plus h minus f of gx whole upon g of x plus h minus g of x into g of x plus h minus g of x whole upon h. What did I do? I divided and multiplied by g of x plus h minus g of x. Right? Now see what is the next step. Limit of the product is product of the limits. So I can write this as limit h tends to 0, f of x plus h or f of g of x plus h minus f of gx whole upon g of x plus h minus gx. Fine. Multiplied by limit h tends to 0, g of x plus h minus g of x whole upon h. Right. What is this? Just see. Limit h tends to 0, g of x plus h minus gx whole upon h is g dash x. So this portion is g dash x. Fine. What is this? Well, I know limit h tends to 0, limit something tends to 0 where that something, okay, let me connect it over here. This something is sitting in the denominator. This is tending to 0. g of x plus h minus g of x whole upon h, where this h is tending to 0, gives you g dash x. Over here, what is happening? Now see, here the denominator I don't know is tending to 0 or not. What can we do is, if h tends to 0, h is tending to 0, my claim is g of x plus h is tending to g of x. Why? Why? What is the reason? G is a differentiable function throughout its domain. That means G is a continuous function throughout its domain. Therefore, limit of G is G of limit. That is the best part about continuity, that limit and the continuous function can interchange with each other. So, what I have written is, if limit h tends to 0, g of x plus h is what? G is a continuous function. This will be g of limit of h tends to 0, x plus h. Polynomial function, continuous, limit of fx is, limit at 0 of f of x is f of 0. So, limit of x plus h is 0 plus h, which is h, or x plus 0, which is x. So, this will be just g of x. So, if h is tending to 0, g of x plus h is tending to g of x. G of x plus h is tending to g of x means g of x plus h minus g of x tends to 0. So, if h tends to 0, g of x plus h minus g of x tends to 0. Because see, as h is tending to 0, g of x plus h is tending to g of x. If g of x plus h is tending to g of x plus h minus g of x tends to 0. Right? So, I have successfully been able to show that here the denominator is also tending to 0. This can alternatively be written as g of x plus h minus g of x tends to 0. Or like we just discussed, g of x plus h tends to g of x. So, if h is tending to 0, g of x plus h is tending to g of x. So, either tend h to 0, then also same thing will happen, or tend g of x plus h to gx, then also same thing will happen. This is f of x plus h, f of g of x plus h minus f of gx whole upon g of x plus h minus g of x multiplied by g dash x. Now, if you remember the definition of differentiability of a function at a point, fx is said to be differentiable at x equals c if limit x tending to c, fx minus fc upon x minus c exists finitely. This is what? Let me say this is my variable fx minus fc upon x minus c as x tends to c is f dash c. Isn't it? This is what is f dash c. C is my gx into g dash x. Don't forget, I had taken x to be a specific number. That is why g of x is a specific constant which is playing the role of c. Whereas because x is a specific constant, h is varying, x plus h is varying. So, g of x plus h is varying. So, g of x plus h is acting as the variable f of x minus f of c, g of x is c, upon x minus c. This is variable, this is constant. As x approaches c, this is variable, this is constant. This is f dash gx into g dash x. This is existing or not existing. Of course, g is a function, x is in the domain of g. So, g of x is a finite real number sitting in the domain of f and therefore domain of f dash. But if it is sitting in the domain of f, f is differentiable at all points of its domain, therefore f dash of gx exists finitely. So, this is existing finitely, so I can replace this limit by f dash gx, and this limit already is existing finitely because g is differentiable at all points of its domain, so I can replace it by g dash x. Because there is nothing specific about the x which we chose specifically to calculate the right hand derivative of FOG at that x, that is why this result is true for every x in the domain of FOG. Understood? Similarly, if you are going to calculate the left hand derivative also, it is going to come out to be exactly the same, and this is a constant value. It is a finite real number which it is coming for every x in the domain of FOG. That means left hand derivative of FOG at any point of its domain is equal to right hand derivative of FOG at any point of its domain, which is a finite value, and that is why FOG is differentiable at all points of its domain, and at any point the differentiation of FOG with respect to that point is this. Differentiation of FOG at that point is given by this formula, and that is why this is what is the proof of the chain rule. So we'll write, therefore, FOG of x is differentiable for all x belonging to domain of FOG, and FOG dash x we have learnt is what? F dash gx into g dash x for all x in the domain of FOG. In the next lecture, we will be learning another perspective of this chain rule and learning about some illustrations which are really important. I'll see you in the next lecture. That's it from my side. Thank you.